As you probably are aware, we're in our 7th week. That means the course is 60% of the way complete. At the end of this week, it'll be 70% of the way complete. The final exam is effectively in the, it sounds very loud to me. Is that too loud or? Okay back there? Okay. Yeah, well, the final exam is effectively in the 11th week of class. That means in 4 weeks' time we will have a final exam. And so to a certain extent that means we can relax a little bit because it is 4 weeks away. On the other hand, there is a lot of material coming through, I think. We're in chapter 4 at the moment on sensation, and I think you'll find a lot of material there as well as in chapters 5 and 6. So do keep up with your reading and studying so that when the final exam finally arrives in 4 weeks' time, it's not going to be a big surprise. So we're in chapter 4 at the moment. So are there any questions before we start in on today's lecture? Okay. Sensation Part 3. Where we left off with last week was a discussion of hearing or audition, and I want to recapitulate briefly some of the physical aspects of sound stimuli, just to remind you of where we left off. So, sound waves is what we were talking about, and we noted that they can vary in their amplitude and in their frequency. If they are pure tones or sinusoids, these will create vibrations of our eardrum, and these will be transmitted to the cochlea by bones known as the ossicles. And inside the cochlea we find hair cell receptor neurons that will signal vibration caused by sound pressure waves. So we're making our way through this, and we got, I think, to the amplitude and the frequency. So briefly, here is a pure tone sinusoidal wave. You can see it has a regular up and down, and the period is the duration between successive peaks, or effectively how long it takes one full wave to be created. And the other word for that might be wavelength. And then the amplitude is simply, well, how much of it we've got. And we can vary both the frequency, low and high frequencies, and the amplitude, high amplitudes and low amplitudes. The low frequencies typically sound like low notes. Higher frequency stimuli typically sound like high notes. Loud and soft are the corresponding perceptual correlates of amplitude. So again, here's our table of frequencies of things that we may recognize. And again, the top note of a grand piano, which is a fairly high note, really is only 4,000 hertz. Little children can hear up to, say, 25,000 hertz. Now, the prefix for 1,000 is kilo, so some people might say 25 kilohertz for that top. People who are a little bit older might be limited a little bit in the range of frequencies to which they're sensitive, so you might only be able to hear up through 20,000 hertz or 20 kilohertz. Once you get all the way down to 20 hertz, which is now the opposite end of the spectrum, you're now talking about frequencies that are so low you can barely hear them rather than so high. And if you don't hear them, sometimes if they have a high enough amplitude, you can feel them. These are known as infrasounds. And the bottom note of an organ, which if it's played loud enough, can be felt if not heard. So the waveforms that we encounter traveling to our ears through a medium such as air, or if we're swimming underwater, the water, something like that. These are not the simple sinusoidal waves that we looked at before. Rather, they are complex waveforms that are combinations of many, many, many sine waves. And here are examples of complex waveforms for a musical and a speech stimulus. So what is happening then is that we have these sound pressure waves traveling to our ears from sound sources in the environment. And, well, we need to transduce these sound pressure waves so that we can sense them and respond to them. And that's the function of audition. So we're now going to get a little bit of anatomy of the ear. And we'll find that there is a structure called a basilar membrane within the cochlea. And this contains hair cell receptors that effectively are stimulated by the sound pressure waves arriving at the ear. And here we go. We'll spend several minutes on this diagram. There are two diagrams here, in fact. Are we having picture labeling questions on the final exam? Yes, we are. Hint, hint. Here we go. Here is the ear, or outer ear, or pinna, P-I-N-N-A. And you can see that, well, somebody's listening to musical notes. And the musical notes are effectively sound pressure waves that are varying as time passes. And these sound pressure waves cause the eardrum, otherwise known as a tympanic membrane, to vibrate. And so here it is down in this lower diagram, a little bit larger now. And you can think of it as the head of a drum vibrating in response to sound waves. And the middle ear is a section of the ear immediately behind the eardrum, and it contains three bones. These are known as the ossicles. And the three ossicles are effectively transmitting the vibration of the eardrum to what is known as the oval window of the cochlea. And this snail-like thing over there is the cochlea. And what we want to do is transmit the vibrations of the eardrum to the cochlea. And how that happens is, well, they're transmitted in the middle ear through the movements of three bones, the malleus, the incus, and the stapes. And the English terms for these three bones are the hammer, the anvil, and the stirrup. So if you like Westerns, well, that's the way to think of it. The hammer, the anvil, you know, you're creating horseshoes or something, and then the stirrup, the guy starts riding the horse. In Latin, though, malleus, incus, stapes. And so this thing is going back and forth, and these little bones are jiggling in response to that. And you can see that the stapes is attached to the cochlea, and where it attaches is an oval window, and effectively there's this membrane that will be vibrating on this base end of the cochlea. And that will cause liquid inside the cochlea to vibrate. And there's effectively this sort of salt water jelly type stuff inside the cochlea, and it is vibrating as a result of the vibration of the oval window, and that's vibrating as a result of the vibrations, the movements of these tiny bones, and that of course is vibrating as a result of the movement of the tympanic membrane, and that of course is caused by the sound pressure waves impinging on our ears. So does everybody see how that chain of vibration works? Good. Now, if we were to take a cross-section of the cochlea, and that cross-section, that slice is shown right here, well, we would find that the cochlea is a fairly complicated structure. There's a tube here, a tube there, and then between the two tubes, we find the primary sensory organs, these hair cells that are pointed out right there. And these lie in a structure known as the organ of Corti that lies on top of the basilar membrane. And the basilar membrane is sort of this sheet that travels the length of the cochlea from the base up to the apex. So the pressure waves are effectively moving from the base to the apex, and what you should picture is this basilar membrane vibrating as a consequence. And sitting on top of this basilar membrane are the hair cells, and they will be vibrating as a consequence. Can they transduce the vibration into a nervous signal? The answer is yes, and we will see how that works. So let's see. Here we now have a closer up view of effectively the organ of Corti. And the organ of Corti, again, is the organ that sits directly on top of the basilar membrane, which is shown here right there in blue. And on top of that, well, what we'll find is one row of hair cells, and these are the inner hair cells. And you can see these darker purple places, those are the actual hairs on top of the inner hair cells, or stereocilia. And then over here, there are effectively 3 rows of outer hair cells, and they also have hairs out their tops, stereocilia. And interestingly, there is a membrane atop all of that called the tectorial membrane. And it turns out that the hairs of the outer hair cells touch the tectorial membrane, and the hairs of the inner hair cells do not. Furthermore, it turns out that there is a large number of efferent axons traveling towards the outer hair cells. That means there are fibers from the brain traveling towards the outer hair cells. That doesn't sound like a sensory organ to me. Isn't it supposed to be the other direction? Well, it is. There are fibers from, effectively from signaling the results of these inner hair cells traveling to the brain. It turns out that it is the inner hair cells that vibrate and transmit information up to the brain, not the outer hair cells. So here we have a nice micrograph, and again you can see here is our tunnel of Corti, which is a space dividing effectively where all of the inner hair cells are. And here we have inner hair cell, and then we have outer hair cells, OHC1, 2, and 3. And again, these guys come in 3 rows, and it turns out that they are controlled in their properties by the brain. These guys, on the other hand, turn out to be vibrating, and they send information to the brain. Here's a close-up of the stereocilia, or the reason why these are called hair cells. These are the inner hair cell stereocilia, seen very close up. And it turns out that these are not attached to the tectorial membrane, which is that flappy stuff right above the hair cells. These guys, on the other hand, are the outer hair cell stereocilia, and these are attached. Now, does anybody have an idea why we have outer hair cells receiving signals from the brain that are attached to that tectorial membrane? Does anybody see a reason why that might be the case? Well, we have these things running the entire length of the cochlea, starting from the base and all the way to the tip, the apex. And it turns out that people believe, at least, that the brain sends signals to different parts of the cochlea to try to either damp down the vibration or to loosen things up and allow more vibration. In effect, the brain tells the outer hair cells whether they should be more pliable or be more stiff. And that influences the properties of the hearing sense. So, I don't want to say anything more about that at a moment. What I do want to talk about is how these guys work to generate a nervous signal in response to sound pressure waves. And there they are, and you can see there's 3 rows, tall, medium, and short. And it turns out that these rows are connected to one another by these tip links. And there we are, tip links. So here we have a tall, a medium, and a short. And you can see these tip links, which are effectively these fibers that join the tip of one cilium to the cilium of next greater size. So those are the tip links. And it turns out that these tip links are very important in controlling the function of the inner hair cells. And the next diagram shows how that works. At the top, we have an inner hair cell. And the inner hair cell has 3 of these hairs, 3 of these cilia, short, medium, and long. And there are these little links that connect the top of the short guy to the medium, and the top of the medium to the long. And usually at rest, you will find potassium ions floating around in the extracellular medium, and the hairs are not bent, and they turn out to be potassium ion trapdoors. These are all closed. So what happens when these things start flapping because of the sound pressure wave vibrating the cochlea? Well, these tip links will effectively pull open potassium channels, and the potassium ions flow into the inner hair cell, and this causes a depolarization, and this depolarization can cause the release of neurotransmitters, which then can cause the generation of action potentials. So that's the basic mechanism of transduction. We have these little hairs flapping around due to the vibration, and every time they flap in one direction, these little doors open, letting in the potassium ions, and that causes depolarization and eventual action potentials sent up to the brain. So that's auditory transduction by inner hair cells. And it turns out that the inner hair cells are stimulating the dendrites of spiral ganglion cells. So here's an inner hair cell. These are dendrites, these yellow guys, of spiral ganglion cells. And these are what will end up transmitting information to the brain concerning the auditory stimulus. Again, you see a large number of efferent fibers controlling the behavior of these outer hair cells. So, that's our look at transduction for the minute. We want to know how it is that pitch is coded by the auditory system, and people have come up with two primary means of explanation. And the first is known as place theory, which is proposed by Hermann von Helmholtz, a famous German psychophysicist, a physicist in fact. And he stated that pitch depends on the place along the length of the basilar membrane where we find the greatest vibrations, the stimulation of the greatest amplitude. And it turns out that different places along the length of the cochlea, along the length of the basilar membrane, different places are more responsive to particular frequencies of sound vibration. And these different places, when stimulated, generate particular pitch sensations. So, and I'll show you a diagram of that shortly. Before we go there, though, the other theory is known as frequency theory. And the idea here is that the perceived pitch, whether it sounds like a low note or a high note, depends on the firing frequency, the firing rate of the auditory nerve. And you can see that, well, if we have the tip links opening and closing those potassium ion channels, that at least if the sound vibration is slow enough, we should be able to generate signals that are effectively locked to the sound pressure wave as it is more intense and less intense. And it should be possible for the auditory system to effectively fire once per wave of sound pressure vibration. And at, well, low enough frequencies, that is true. If you have, say, 100 cycles per second, and that's a fairly low note, that's about the fundamental frequency of my voice, say. If you have 100 cycles per second, then it turns out that, yes, the inner hair cells and the spiral ganglion cells can follow the vibration at that relatively low rate and send one action potential every 100th of a second, namely 100 action potentials every second, keeping up with the auditory stimulus. If we change that 100 hertz tone to a 200 hertz tone, so it's now a higher pitch, well, turns out that there are hair cells and spiral ganglion cells and whatnot that are able to fire at twice their original rate, keeping up with the 200 hertz stimulus. it turns out that yes, the frequency of firing by neurons coding auditory information does help us understand perception of different pitches, up to the point where neurons can actually fire fast enough. Now it turns out that a lot of neurons cannot really fire faster than, say, 400 action potentials per second. At that point, that's just too many action potentials. You can't go to 500 or 600 or 1,000, or we were talking about 20,000 hertz as the highest note that young people can hear. There's no way you're going to get a neuron firing at 20,000 times per second. It's simply too high. The fastest neuron might be closer to 400 action potentials per second. So frequency theory effectively helps us understand the perception of pitch at lower frequencies. Place theory, on the other hand, can go beyond that low frequency range. And this is the way the place theory works. Again, we need to consider this cochlea, which is a snail-like structure, and we want to consider how stimulation varies as we move from one end of the cochlea to another, from the base end, where we find the initial stimulus at the oval window, the base, all the way up to the tip, which is that guy right there, or apex, the apical end of the cochlea. So what we're going to do is take that cochlea and stretch it out. So we have the base all the way to the apex, and it turns out that low frequency vibrations are able to travel the farthest. Medium frequency vibrations are not able to travel as far. High frequency vibrations only travel short distances. Now, this is more or less a fact of physics, and you're probably familiar with it, intuitively at least. Let's say there is an earthquake, and you feel this sort of slow rumble. You're sort of going like this. What kind of earthquake was that? Was that a close earthquake or a far away earthquake? A sort of slow rumble. That is a far away earthquake. That's the kinds that we prefer. Now, what if you have one of these sharp jolt earthquakes like this? That is a close earthquake that you do not want to be in. And it turns out that when you have these slow, rumbly things, well, that's a whole bunch of low frequency energy, and the low frequencies are able to travel long distances. So when we receive an earthquake and we feel it very slowly like this, well, that's because that earthquake is far away and those low frequency waves are able to travel that distance. On the other hand, if we feel sharp jolts, well, it turns out that there's a lot of high frequency energy there. If we feel all of that, we must be really close. It's just a fact of physics. Low sounds travel farther, low vibrations. So what we can do then is say, well, if we have neurons, the inner hair cells responding really well towards the apex of the cochlea at this end, hey, well, it must be a low frequency stimulus that we are hearing. So we have a low pitch perceived in consequence. On the other hand, if we have greatest stimulation very close to the base end, well, we'll probably say, yeah, that's probably a high frequency thing. They just couldn't get those high frequency waves to travel any farther. So we get a best stimulation here at the base end, and we say, well, it's a high frequency sound that we are listening to. So we'll hear a high pitch. I think of this as a reverse piano theory. So the piano, again, the low notes are on the left and the high notes are on the right. This is a reverse piano theory because the low notes are on the right and the high notes are on the left. So effectively, the cochlea is laid out as a reverse piano. And you can use the location of maximal stimulation to determine the frequency of the stimulus. That's place theory. Does that make sense, place theory? Good. Now let's see. So, in total, evidence suggests that both theories are correct, and the perception of the higher frequencies in particular depends on the place where the basilar membrane is stimulated best. At lower frequencies, though, we can actually rely on the rate at which individual neurons are firing, the rate at which we're receiving action potentials and that's the frequency theory. So effectively we have this hybrid theory where we have one kind of explanation for the higher frequency stimuli, the higher notes, and another kind of explanation for lower frequencies, the lower pitches. Does that make sense? Good. Okay, so what we want to do is move away from the cochlea into the brain. And so it's important to know that the inner hair cells are sending signals through spiral ganglion neurons. And here are the spiral ganglion neurons, and they send effectively their dendrites into the cochlea, where the dendrites of the spiral ganglion cells are stimulated by the inner hair cells. And the axons of these spiral ganglion cells travel into the brain, into the brainstem, where we find the cochlear nucleus. Now, this cochlear nucleus here, I should point out, is present on this side of the brain, the left, and on that side of the brain, the right. So we have two ears on left and right, so we have two cochlear nuclei, one on left, one on the right. Now, this is showing what's happening to the transmission of information concerning left ear stimuli. So the auditory nerve formed by the axons of the spiral ganglion cells, the eighth nerve, that was cute. Effectively sends its axons to the ventral cochlear nucleus, where it makes contact with neurons that send their axons to the superior olive, both ipsilateral and contralateral. Neurons in the superior olives on the same and opposite sides of the brain in turn send their axons up these fiber bundles known as the lateral lemnisci. Now it turns out that the dorsal cochlear nucleus neurons are also innervated, and these also send fibers up the lateral lemnisci on either side of the brain, so that by the time we reach the inferior colliculi on the left side of the brain and the right side of the brain, and now this is the midbrain. This is underneath the thalamus in the midbrain in the mesencephalon. In the inferior colliculus, we get two kinds of fibers, effectively fibers from the olive, the superior olive, and fibers from the dorsal cochlear nucleus. And it turns out that by this point, we have inferior colliculus neurons that are receiving information from both ears. Now, I don't know if you can see these wiring diagrams, but you can see that we have these fibers going to ipsilateral, superior olive, and contralateral, and then they go up to the inferior colliculus. And we also have fibers from the dorsal cochlear nuclei, ipsilateral and contralateral. So by the time we're at the inferior colliculus, we are talking about neurons that receive input from both ears. What is that good for, do you think? Why do we want input from both our ears? Well, for one, it helps us figure out where a sound source is located. And in fact, if we want to know where a sound source is, one of the best ways to proceed is to compare the stimuli that we receive in our two ears. So for example, if somebody in the back were to start talking, the sound waves would come to me, and my ear that is facing you in the class, in particular the back of the classroom, will receive sound pressure waves. And this ear that is facing in the opposite direction, towards the screen, will also receive sound pressure waves. Which sound pressure waves will be louder? The ones facing or the ones facing the opposite direction? This guy right here. It's facing the sound source, so it's going to receive more intense sound pressure waves. So one simple way to figure out where a sound source is located is to compare the intensity of the stimuli received by the two ears. The ear that faces the stimulus is pointing in the correct direction, in a sense. a second important thing. It turns out that it takes time for sound to travel. Everybody knows about the Mach numbers and all the jet planes. They're going Mach 1 and Mach 10 and all this. Fine. Sound travels very quickly, but it still takes a finite time in which to travel distances. And it turns out that if somebody is talking back there, the sound stimulus will arrive at my close ear sooner than it arrives at my far ear. So not only is it louder, it's also sooner. So what I can do is now compare the arrival times of the sound stimuli in the two ears. And those are the two primary comparisons made to help us know where a sound source is. Number one, compare the intensities in the two ears of the stimuli. Two, compare the times of arrival. So, a lot of this spatial processing, in its early stages at least, is done early on in the auditory system. And this is made possible by the fact that neurons in these low-level areas are receiving input from both ears. So, it turns out that the neurons in the inferior colliculi, in the mesencephalon, have axons that travel up to the medial geniculate nuclei in the thalamus. And you know about our thalamus. It is a sensory way station. We saw that with senses, the chemical senses, in the previous lecture. Well, today we have audition, and we have the neurons arriving from the inferior colliculus neurons showing up in MGN, medial geniculate nucleus. And the MGN neurons project to auditory cortex. And that's shown by these red fibers here. And of course, this occurs in both hemispheres. Now let's see. Auditory cortex. Well, we would like to know more about auditory cortex. It's actually fairly complicated. We not only have primary auditory cortex, which is sort of buried under the fold here, inside this fissure, and there it is sort of blown up. We have these surrounding areas of cortex close to A1, close to primary auditory cortex, that are clearly also heavily involved in processing auditory stimuli. Some of them seem more devoted to figuring out what it is we are hearing, so that they are interested in recognizing something by its sounds. Other neurons in these areas of the brain, in say secondary auditory cortex, are interested in figuring out where the sound stimulus is. So we effectively have these two systems. What is it that we are hearing? Second, where is this thing that we are hearing? Primary auditory cortex, though, is right here, and it is the first place where the medial geniculate neurons are sending information, and it is organized in what is called a tonotopic fashion. And a tonotopic organization means, in this case, that as we move along the surface of A1, we encounter neurons that vary in their frequency preference. And so, what we have on this little A1 zone here is a map, and this little map is a frequency map, and this says 500 hertz, 1,000 hertz. 1,000 hertz is 1 kilohertz. So that's 1 kilohertz, 2 kilohertz, 4, 8, 16 kilohertz. These are relatively low frequencies corresponding to low pitches. These are very, very high frequencies over here. And the idea is that neurons, as we move from the left to the right in this picture across A1, vary systematically in their frequency preference. So these are the neurons corresponding to 500. These are the neurons, this is where they live if they're responding to 16 kilohertz. And you can see that this organization more or less parallels the organization in the cochlea. So remember how the cochlea, we had a sort of frequency progression. We had the low frequencies best represented over here at the apex, and the high frequencies represented best here at the base of the cochlea. And this is the same arrangement, except in reverse order. And high frequency sounds then stimulate best the base, and that's represented here. Low frequency sounds stimulate the apex, that's over here. And so there's a progression in best frequency as we move along the basilar membrane. There is a progression in the best frequency as we move along from one end of auditory cortex, primary auditory cortex, to the next. Okay? So there's this frequency progression. That's all we're trying to say. And that is what is meant by a tonotopic or cochleotopic organization. Does that make sense? Good. Here's some data from some poor cat they did this experiment on. In fact, we have at UC Irvine one of the best places in the entire world for studying auditory function, the study of hearing. The Center for Hearing Research has a number of faculty from a variety of departments, not only on that side of campus, but also on this side, I'm happy to say. And we do have one professor in particular who has done a lot of work with cat physiology, named Professor Middlebrooks over on the other side of campus, who's world-renowned for figuring out just this sort of thing. So what you do is you put in a microelectrode at different locations in primary auditory cortex of cat. And of course, the cat brain is different shaped, it's small. You know, primary auditory cortex in a cat is not the same location as it is for our brains. In any event, it's right here, say. You insert the microelectrode at different locations in primary auditory cortex, and then you play notes, you play tones, you play auditory stimuli that vary in frequency. And you try to figure out which frequency a particular neuron likes best. And how do you do that? Well, you simply measure the rate at which it produces action potentials. You measure its firing rate as a function of the auditory stimulus frequency. And if you were to do that, you would find, well, over on this end, the best auditory frequency for stimulating neurons is pretty relatively low, 3.3 kilohertz. Now, these numbers are in units of 1,000 hertz, so that's 3.3 kilohertz. And as we move in this direction, we get successively higher frequencies. So over here, well, there's 22 kilohertz. That is the optimal frequency for stimulating a particular neuron in that particular location. So again, there's a tonotopic organization. In this cat, we have low frequencies preferred over on the right side, high frequencies preferred here on the left side. So once again, a tonotopic organization, reflecting the way that frequencies are laid out in the cochlea. So, that's more or less what I wanted to say about audition. Are there any questions about audition before we move on to vision? Well, let me move on then. Vision, of course, refers to seeing, so this is our sense of sight. It's our primary distance sense. It allows us to detect and recognize and respond to things that are distant from us. And as you know well, the stimulus providing this information is light. And light varies in intensity and in wavelength. It turns out that light can be thought of in two ways. And we're going to use both of them in what follows. One way is as a wave. So we can talk about light waves. And we can think about waves as having wavelengths. And in particular, we'll find that, well, as we vary the wavelength of a light, we'll get a different color. We can also say, well, the waves vary in intensity, and the more intense, the brighter the light appears. Okay, so when we speak about light as waves, well, we have the intensity or amplitude, and we have the wavelength and perceptual correlates. But it turns out that we can also think of light as particles. These particles are called, what are they called? Photons. P-H-O-T-O-N, photon. In any event, when we think about light as particles, it's actually much easier to understand how the transduction of light energy occurs. Effectively, these light particles arrive in the eye, they stimulate particular structures that we'll talk about shortly, and wham, we end up seeing something as a result of the ensuing nervous activity. So, light we'll think about both as waves and as photons, particles. So we have light entering the eye. Big structures include the cornea, the iris, and the lens. These control the amount of light entering the eye, and they help form a focused, crisp image on the retina at the back of the eye. And that's where the photosensitive elements lie. And we'll see this in a large number of pictures. So let's see. Let's start with the physical stimulus. So the electromagnetic spectrum has a very tiny region corresponding to visible lights. So in this particular diagram, we have a white light shown on a prism, and a prism is able to split a white light into component wavelengths. And so these refer to different wavelengths here. These wavelengths are in units of nanometers. So this is sort of nanotechnology for psychology, nanometers. So 400 nanometers, 500 nanometers, 700 nanometers. What is a nanometer? Well, it's a very short distance. How short is it? Well, 1 meter is 3 feet long or a little bit more. It's actually more like 39 inches. So 1 meter is 39 inches, just a tiny bit longer than a yard. If we have 1/1000th of a meter, which unit of length are we talking about? 1/1000th of a meter is a millimeter. Okay, so we would take our meter, we divide it into 1,000 pieces, and we say each one of those pieces is worth a millimeter. Now let's say we have a millimeter, and we divide it into 1,000 equal parts. What unit of length do we then have? A micrometer. So a micro is the prefix for a millionth, in the same sense that milli is the prefix for a thousandth. So we have our meter, then we have the millimeter, then we have the micrometer, which is a millionth of a meter. And what is 1,000th of a micrometer? Nanometer. Okay, so that's effectively 1/1000th of a meter. And that's the units we're talking about. 1/1000th of a meter is a very short distance. And if we have 400 billionths of a meter, that's still a very short distance. So if we have 400 nanometers, yes, that is almost a whole micrometer, but not quite. This is half of a micrometer. That's still very short. This is a little bit longer than half of a micrometer. These are in units of nanometers. And it turns out if we have light wavelengths, electromagnetic energy wavelengths in this range, and we are able to see it due to our vision. If we have wavelengths that are shorter than 400 nanometers, then we typically are not able to see that electromagnetic energy. However, it still exists. And this is where ultraviolet rays live. And as you well know, these can be very injurious if we don't take proper care when we're out in the sun. If we now consider electromagnetic energy with even shorter wavelengths, we get to the energetic X-rays, which are able to penetrate the tissues of our body. And even worse, we can stand beside a nuclear reactor and die with gamma rays or something like that. These are very, very, very short wavelengths. It turns out that they're very, very energetic photons. Now, things get a little lazier on this end because we're talking about longer wavelengths. And one step past visible red light are the infrared rays. Things that are vibrating because they're hot release infrared energy. And there are now infrared cameras out there. Does anybody have an infrared camera? Just out of curiosity? Yeah, well, you can see things based on the heat that they are releasing. And effectively, it's thermal vision in some sense, at least in some range here. Infrared rays are at longer wavelengths than 700 nanometers. Longer still, you're talking about radar waves, and finally you get to broadcast radio waves, and these are, really, really long waves. And they're also less energetic unit by unit than, say, a gamma ray. I actually like this little diagram. The electromagnetic spectrum once again, and now they've reversed the spectrum. So here are the visible lights in the range 400 to 700 nanometers. Now the infrared band is on the left. Here are microwaves and radio waves, the very, very, very long wavelengths, and we can see how long that wavelength is. 10 to the third meters. 10 to the third meters, that's a kilometer. That's like 0.6 of a mile. So you can have radio waves that have a wavelength that is, a significant fraction of a mile long. That's really long. Now, on the other end, we find ultraviolet and blah, blah, blah. Finally, we're getting to cosmic waves and gamma rays, and you get these really, really, really short wavelengths. What is that? 10 to the 11th, 10 to the minus 12th. Really small. It turns out that the energy of a single photon varies from very weak when you're talking about these very long wavelength things, and very strong when you're talking about these very short wavelengths things. Hence the danger of gamma radiation and X-rays and things like that. So, even ultraviolet light is a little bit dangerous. Not only can it affect our skin and give us a sunburn, and too much of that can lead to melanomas and bad things like that. Turns out it also enters the eye, and even though we can't see the UV radiation, structures inside our eye respond to it nonetheless. In a moment, I'll tell you how it can burn out short wavelength sensitive receptors. But before we get there, I'll tell you how it effectively causes the lenses inside our eye to become brown and opaque. So, the lens absorbs UV radiation. This causes the lens to yellow and eventually brown and opaque. And by opaque, that means you cannot see through it, so the eye has become useless. What would you recommend to somebody who has an opaque lens in their eye? Well, some sort of surgery where they pluck out the old lens and put in a new, say, plastic lens that is clear. You can see what happens. We're taking a photograph of an infant's lens. Here we have the photograph of a 91-year-old's lens. Pretty nasty. And here's the moral. Wear sunglasses when outdoors. If you're on the water, you will receive more light than otherwise. If you are skiing in the snow, you will receive more light than otherwise. If you're at a high altitude, you will receive more light than otherwise. Just in general, in Southern California, there's a lot of radiation out there. You should be wearing sunglasses all the time, if there's any sun whatsoever. What about people in Australia? Have you read about the folks in Australia? Well, there's that ozone hole. And the ozone molecules in the atmosphere are really good at absorbing ultraviolet rays. Well, there's an ozone hole caused by fluorocarbons, refrigerants, and a lot of it is concentrated in the area of Australia above our planet. And what that means is people in Australia get more ultraviolet radiation than we do simply because they have less protection by the atmosphere. So they are really, really good at wearing hats and completely covering up, because otherwise they get horrible sunburns all the time. So that was a digression. What do you think about that one? Okay. So here is a picture, finally, a schematic picture of the eye. And, are there going to be picture labeling questions on the exam? Maybe. And if so, this would be a candidate. That's all I'm saying. Something like this. You know, sort of the schematic diagram of the ear, the schematic diagram of the eye. These are fodder for people like me when making exams. Okay, so here's the front of the eyeball, and if you were to touch the front of your eyeball, well, it could be painful. It turns out that there are pain receptors right on the surface of the eyeball. This is called the cornea. And it's transparent, unless there's some nasty scratch or something. It's transparent. Light will pass through the cornea, through what is effectively salt water, these aqueous humors. Aqueous humors. Where did they get that word, a humor, in aqueous humor? It's just salt water. In any event, the light passes through the corneal surface, the salt water, and then it hits the lens. And this lens, for young people at least, is able to change its shape and helps accommodate to viewing at different distances, say near viewing and far viewing. The light continues through the vitreous humors, again effectively salt water, to the back of the eyeball. And at the back of the eyeball we find a layer of nervous tissue, part of the central nervous system, called the retina. And the retina lines the back of each eyeball. And if we are looking straight at something, I'm looking straight at you now, I happen to know that the light waves from you are going to fall at that spot right there, at the back of the eye, along this axis. They're going to fall in what is known as the fovea. And the fovea is the part of the retina that provides effectively the sharpest vision, as we'll see in a moment. And it is what we use when we look directly at something. Why? Because we want to glean as much information as possible. And by looking directly at it, we place the arriving light information at the most sensitive area of our retina, the fovea. Now, it turns out that the retina has a large number of neurons, and the ganglion cells in the retina have axons. The axons travel up to the brain through the optic nerve. And so what that means, it's sort of nasty, but if you think of an eyeball all by itself, there's a little cord coming out the back. And that's the optic nerve. It's carrying the information from the retina up to the brain. Now let's see. There are a number of things going on here in addition. The pupil is, let me start with the cornea. People always say that it is the lens of the eye that helps us focus the light on the retina. It's what provides the clear picture. Well, that's not strictly correct. It turns out that the strongest focusing element of our eyeball is not the lens, but the cornea. And the reason it is the strongest focusing element of the eye is that, well, it is a curved surface, roughly spherical on the front of the eyeball, and it has on one side air, and on the other side salt water. And it is the difference in the refractive indices of air and water that make this curved surface something that focuses light, a refractive surface. How many people remember this sort of thing like Snell's law, indices of refraction, curved surfaces? Oh, good. How many people have taken their year of college level physics? I can strongly recommend taking some kind of physics course. In any event, basically, how does light get bent or focused? You've got to have curved surfaces that are separating substances with different physical properties. In our example, it's air in front of the eyeball and salt water immediately behind the cornea. And it turns out that light effectively likes traveling through air. It likes traveling through the salt water a little bit less. Turns out it travels just a tiny bit slower. And it turns out that this curved boundary between the air and the salt water is going to cause the light waves to bend or to focus, to make a sharper picture back here. How do we know that the cornea is focusing light? How many people have ever opened their eyes up underwater? Now you have water in front of the cornea and water just behind the cornea. Now there's no difference whatsoever between what's in front of the cornea and what's behind it. That means there is no longer any refraction of light, no longer bending of light caused by the cornea. You need to have a difference in the two substances, air and water. But if you're swimming underwater and you open your eyes, now it's just water. So there's no more focusing by the cornea. Is the world very blurry? Yes, the world is very blurry because your cornea no longer focuses light. So the cornea is the primary focusing element of the eye. And let's see, what's that surgery called where they reshape the front surface of the eye? LASIK surgery. LASIK surgery. Why is it effective? Well, the cornea is the major focusing element of the eye, and if you now reshape the cornea, you can improve the focusing power if it's in need of improvement. So, the light hits the cornea, which is the interface typically between air and water, and so light gets refracted or bent or focused. It then passes through a hole known as the pupil. The pupil is a hole. What's surrounding that hole? Well, it's the iris. It's, in a lot of people, brown. In some people, it's blue or maybe green. It's effectively a muscle that is able to contract to make the pupil very narrow. It's also able to dilate and make the pupil very wide. So that's the iris that's doing that. And the light is able to pass through the pupil. It then contacts the lens, and we'll see in a moment. Yes, the lens is able to change its shape. Boom. Eventually, we will get a focused image back here. Now, let me think. Here we are again. Okay. More information. What I want to talk about, I think I'll use this previous diagram. Yeah, I'm going to use this diagram. Sorry about that, folks. I want to talk about the optic disc. Like I said before, at the back of each eyeball, you have a cord coming out, and that cord is traveling up to the brain. And in the eye itself, the beginning of the cord is known as the optic disc. And it turns out that we are unable to see things there. And we're going to have a demonstration shortly showing that, yes, if we were to place an object out in the real world in a way that makes its light fall on the optic disc, then that object will be invisible because we do not sense light at that location. What else? The sclera is effectively the whites of the eyeball. The ciliary muscle will cause the lens to change shape. And I guess that does it for that diagram. Good. Now we're on this diagram. The retina is at the back of the eyeball. It's part of the central nervous system. It lines the back of the eye. And when we look straight at something, the light from that something is falling in the foveal region of the retina. When we consider the cells that are in the retinal sheet at the back of the eye, we find cells arranged in layers. And these have very fancy names like the outer plexiform layer and the inner plexiform layer and what have you. And what have you. But basically, there are rods and cones, which we'll talk about in one layer, and then cell bodies here. We'll have a bunch of dendrites and axons contacting one another in this layer. More cell bodies here. Then we'll have more dendrites and axons contacting one another here. Eventually we get to the cell bodies of the ganglion cells, and it is the axons of the ganglion cells that travel up to the brain through the optic nerve. Now the various cells that they are diagramming for us include rods and cones, amacrine cells, which are going to provide horizontal connectivity in these layers, horizontal cells, which provide horizontal connectivity in these layers, and finally, the reason I like this one is it's showing a Miller cell, which is a very large glial cell present in the retina. So there certainly are glial cells in the retina. And the Miller cells are these very large cells that effectively extend the entire depth of this thin sheet of neurons. Interestingly, here's something to think about. Light comes from this direction in this diagram and has to go through all this business before it hits the rods and cones. And we're going to see in a moment that the rods and cones are where light particles are actually absorbed. And you have to ask yourself, wow, how does light ever travel through all this business and get to the rods and cones? Well, the answer is that in the visible wavelength range, 400 through 700 nanometers, all of this business is transparent. So the light travels through these layers without any problem where it reaches eventually the rods and cones so it can get absorbed. All of this stuff is transparent to visible wavelengths. So the rods and the cones, they're signaling light absorption. And here we have rods and cones. This layer here, the rods are these yellow guys, and the cones are these purple guys. And we'll see in a moment that these outer segments of rods and cones differ in shape, and sort of indicated as a purple cone here, a purple cone there, a purple cone there. So these are cone photoreceptors. And here we have sort of a rod. It's more like a rectangle. Rod, rod, rod. These are all rods. In any event, they transduce light, and they send signals to bipolar cells. And the bipolar cells are these pink guys. And you can see that they make contact with the inner segments of these photoreceptors. And the bipolar cells themselves send contact to the ganglion cells, and that's these light blue guys. And the ganglion cells in turn have axons that travel over to the optic disc and then up into the brain via the optic nerve. So if we were to look for the direct path to the brain concerning the light stimulus, we would say, well, photoreceptors are going to absorb light particles. They then send signals to bipolar cells. Bipolar cells send signals to ganglion cells, and the ganglion cells send action potentials up to the brain via the optic nerve. And that's sort of the direct path by which information is sent concerning the absorption of light. So, why are there rods and cones? Well, turns out the rods and cones do different things. One thing is that they contain different pigment molecules, and these pigment molecules absorb light, and so that the light absorption properties of rods differ from the light absorption properties of cones. But what is common to both rods and cones is that their pigment molecules change shape when they absorb a photon of light. And the change in shape of the molecule is what corresponds to transduction by both rods and cones. So it turns out that rods work in a way that makes them active at low light levels, and you're intuitively familiar with their properties. They are what's active at nighttime, and by nighttime I mean something that is actually pretty rare around here in Irvine and surrounding areas, because there are always these lights out, the street lights and the orange haze in the sky from the cities and what have you. But there are places where you can go where nighttime is really dark. And at that point, you can be certain that only the rods are helping you see. There is no color seen. Everything is a shade of gray. And at these light levels, we're talking about something that's formally known as scotopic vision, mediated by the rods. Now, daytime vision, well, that's mediated by the cones. And I think you'll agree that vision is much sharper during the daytime, and it's a lot fuzzier at nighttime. And it turns out, well, yeah, at daytime there's a lot more light information. The light level is higher, and so we have more photons arriving at the eye. We have more information about the environment. And so we're able to construct a higher resolution picture of the world, so to speak. The second thing that cones provide us, in addition to high acuity, is color. And so in the daytime, we normally see a color world, and that's provided by cones as well. So this is formally known as photopic vision, and is perhaps best for things that we are looking at directly. And again, when we're looking at things directly, light from those things are falling on the fovea. So we now have a cut through the retinal sheet at the layer of the photoreceptors, and it shows, yes, there are rods and cones at most locations on the retina. The rods are these little white guys. The cones are these larger white guys surrounded by black islands. And so at this particular location in the retina, we have both rods and cones present. And that makes sense that, well, we need both rods and cones across the entirety of the retina because, well, during the night, we need to use our rods, and we don't want only half of the world to be visible. We need to have the rods everywhere. But during the day, we use our cones. We need the cones to be everywhere as well, so there are no holes in effect. So at any one point in the retina, it turns out there's almost always a mix of rods and cones present. And remember that these are really small things, microscopic. They differ in the shapes of their outer segments, and the outer segments is where their photopigment molecules are located. The cones, I don't know, it looks sort of like an ear of corn almost. The rods look more rod-like. So they differ in their morphology. They also differ in their distribution across the retina. It's true, what I just said, that generally you will find both rods and cones at every point on the retina. However, sometimes there are more cones than rods, and sometimes there are more rods and cones. It all depends. This says exactly what the story is. This tells us the distance on the retina away from the fovea in degrees of visual angle. Now let me explain degrees of visual angle. Always use one eyeball when you do this. Okay, so I've covered up one eyeball, and I'm holding my thumb out straight ahead, and I'm looking at my thumbnail, and I happen to know that my thumbnail's image is being formed on my fovea of this open eyeball. Fine. That straight ahead direction is 0 degrees of visual angle. That's the origin for measuring degrees of visual angle. Now let's suppose I continue to look straight ahead. I'm looking at that exit sign now, and I move my thumb way over there out 90 degrees to the side. What angle is that? 90 degrees to the side, okay? So this would be, if that straight ahead is 0, then that's 10, 20, 30, 40, blah, 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 90 degrees over to my right side. You can do the same thing for left side, 90 degrees to the left. You can also go up and down. So if this is 0 degrees straight ahead, this would be 90 degrees up, 45 degrees up, 45 degrees down. These are degrees of visual angle. Now, for each degree of visual angle, there is a corresponding location on the retina. That's the important thing. And if we measure the number of rods and cones at these different locations on the retina, then we get a result like what's shown in this slide. So at 0 degrees of visual angle, well, that is the fovea. And what do we find at the fovea? Well, you see these blue curves? That's telling us how many rods there are. Uh-oh. How many rods are there at the fovea? 0. It turns out that right in the middle of the fovea, there are no rods. The only thing you get is a very large number of, what does the red curve show? Cones. Right. So when you look straight at something, in the very middle of the fovea, the only thing that is there to absorb light are the cones. If you want to see something with your rods, the light must fall outside of the fovea. And you can see that the rods have their greatest density maybe 15 degrees away from the fovea. So if this is 0 degrees for that eye, 15 degrees might be way over there. So light from this direction that I'm not even looking at, that is what's going to be the best direction for the rods. In the fovea, when I look directly at something, there are no rods. It's only cones. And this makes sense possibly if you've ever looked at very faint stars. How many people have noticed faint stars disappearing if you look straight at them? Well, they do. If you have a very good night where you're able to look at stars, which isn't always the case around here, sometimes you'll get the idea that there's a faint star and then you'll look directly at it and it disappears. The reason is the faint star is providing a very low level of light. If you have a very low level of light, which system will you use to see it? The rods or the cones? The rods. Now, if you look directly at something, a very faint light, are there any rods? No. The only thing in the fovea right in the middle are cones. So, if you have a very faint star and you're trying to see it, well, don't stare at it directly because you won't see it because there are no rods in the fovea. If you want to see a faint star, you look slightly to the side. Has anybody ever noticed that? Good. If you want to see something faint, look slightly to the side at nighttime. Good. So there we are. The cones, there's millions of cones in the fovea. There's even more millions of rods if we now go into the periphery, away from the center of gaze. So we are now just about the point. Oh, let me say one more. Yeah, let me say one more thing. One more thing. The axons of the ganglion cells in the retina travel up to the brain. They travel up the optic nerves, those little cables at the back of each eye. And the optic disc is the place where they exit the back of the eyeball. And the optic disc, the optic nerve head, is often used by ophthalmologists and optometrists to figure out a person's overall health. As there are certain things that can go wrong with this area of the eye for somebody, say, who's suffering from diabetes or high blood pressure or what have you. So you know how the person's looking in your eyeball like this. Frequently, they're looking at the optic nerve and seeing if there are any irregularities. They're looking at your vasculature to see if there are any blood vessels that look damaged or injured. Anyway, the optic nerve is all axons. And that means there are no photoreceptors that would absorb light there. So if we have an image on the optic nerve of something out in the real world, we will not see that thing out in the real world. And what I'd like to do in the last moment is have you all demonstrate to yourself that in fact we cannot see things placed at the optic disc, the optic nerve. So would you please join me in the following? Go like this, cover up one of your eyes, hold up your thumb. Now what I'm going to do is I'm going to choose somebody that is lined up with my thumb. So I'm actually looking at you, and I'm going to move my thumb about 6 inches horizontally until it disappears. No, you're moving it too fast. 6 inches slowly. So I'm looking at that person right there. I'm not changing who I'm looking at. Oh, that's where my thumb disappears. So that's the difference between here and there. I don't know what that distance is, but it might be about 6 inches. How many people see their thumb disappear? Good. The image of the thumb is falling on the head of the optic nerve, and there's no photoreception there. You can do this with the other eyeball. Like this, move there, boom, invisible thumb. So we'll start in again next time on transduction. Please keep up with your reading in Chapter 4. Thanks.